Hi everyone, this is going to be Math 103 Lecture 24. And today we'll continue our study of Taylor series. So let me recall what the Taylor series of a function looks like. Let me start with center 0. So recall that if f of x is a function, then the Taylor series for f of x centered at x equals to 0, or a equals to 0, usually we use the letter a for the center, is the following power series. So it's the sum, n goes from 0 to infinity, of the nth derivative of the function, and this is what this symbol means, evaluated at 0 divided by n factorial times x to the n. So this is kind of like a polynomial, but it's kind of infinitely long polynomial. If you want to expand this out, here's what the first few terms looks like. First term is f of 0, the function value at 0, and then there's the linear term, the first derivative divided by 1 factorial times x, the second derivative divided by 2 factorial times x squared, and so on. So notice here that we use the convention that 0 factorial is 1. Because here the range of n is from 0 to infinity, and so we need to make sure we understand what 0 factorial is. And it turns out that the right convention to use for 0 factorial is that 0 factorial must be 1. Another observation worth remembering that also shows up in the case when n is 0 is that the 0th derivative of a function is the function itself. So this is what we used here, because when n is 0, we got the 0th derivative of the function evaluated at 0, which is exactly f of 0. And then x to the 0 was 1, that's why I didn't write it. And n 0 factorial is 1, that's why I didn't write it. That's why when n is 0, this term here becomes f of 0. So what's the point of Taylor series? Well, the Taylor series is supposed to be a nice power series model for the function, because the original function f of x here, like this function here, we have no control on what this function may be. It could be some complicated function. But the Taylor series, these are just numbers. So it's just powers of x that are playing a role. And so the hope is that that Taylor series will converge to the function f of x. And so in general, the Taylor series converges to the function f of x, at least near the origin, at least near x equals to 0. Now what do I mean? So here I'm considering Taylor series centered at 0, so this is why we expect convergence of Taylor series to the function itself near x equals to 0. So here's what I mean. What I'm saying is that we actually expect that the Taylor series, which is the sum here going from 0 to infinity, nth derivative of 0 divided by n factorial times x to the n. What I'm saying is that this series will converge, and the value of this convergence series will actually be the function value f itself. Okay, so let me call this relation star. So this is kind of remarkable, because like I said, f of x could be an extremely complicated function, like sine x, whereas on the right-hand side, we just have powers of x. So note again that these numbers, these coefficients that you see in front of the Taylor series, these are just numerical values. You just take the nth derivative of the function, you plug in 0, and then you divide by n factorial. So really, you should think of power series, which basically just means this, as infinitely long polynomial. And the amazing thing is that function, as complicated as it may be, the amazing thing is that the Taylor series will converge to the function value itself for all x near 0. So for all x on an interval around 0. This is the general situation. Of course, for some functions like e to the x, the Taylor series converges to e to the x for all x. So what does this mean? Let me just sort of explain what this means. The fact that the Taylor series converges to f of x for all x on an interval around 0, it means the following. So this means that there is some number r, there exists a number r such that this relation here, star, holds true, or rather the star is correct. So yes, the star, this equality holds for all x, with between minus r and r. So this r is known as this r is known as radius of convergence. Known as radius of convergence. And oftentimes you can obtain this value r by using the ratio test. You can use the ratio test oftentimes to note to figure out for which value of x the series here will converge, and usually it's going to be some number r. And then in this interval, it converges. So, so this minus r to r is also known as interval of convergence. Is known as interval of convergence. Okay, great. So sometimes when you get the value r here, you'll know that on this open interval, the Taylor series converges. But sometimes for the endpoints, like r and minus r, you might have to do kind of manual work, like see what happens when x is equal to r. So endpoints sometimes need a special, they need to be taken care of manually. But at least on the open interval, usually you get convergence. So again, the Taylor series is supposed to be a tool that represents the given function perfectly. And last time we actually gave an example of a bunch of functions and their Taylor series. And one of them we saw was for sine x. So we computed the Taylor series for sine x around 0, and this was the series we got. So sine x is equal to x minus x cubed over 3 factorial plus x factorial divided by 5 factorial minus x7, or x to the 7 divided by 7 factorial plus x to the 9 divided by 9 factorial, and then minus, and so on. So the pattern is that it's alternating, and that only odd powers of x are involved. And the corresponding power, for each corresponding power of x, you're dividing by that power factorial in the denominator. So this was a Taylor series. And if you like, you can write this in the sigma notation as follows. It's from n equals to 0 to infinity minus 1 to the n times x to the 2m plus 1 divided by 2m plus 1 factorial. Okay, so now let's look at this example closely. So when we take Taylor series, we can truncate it. We can truncate it at a certain point and just kind of get Taylor polynomials instead. So when you take a Taylor series and truncate it by taking it up to a certain number of terms, you get something called Taylor polynomials. So when you truncate Taylor series, you truncate Taylor series by taking only the terms up to a certain power of x, power, sorry, oh, it's better, certain power of x, we obtain something called Taylor polynomials. Okay, so let's look at an example of sine x again. So it's basically the first Taylor polynomial for sine x is going to be just by taking the first term, so x. The t3 sub x is the Taylor polynomial of degree 3, and it's going to be x minus x cubed over 3 factorial. And the order 5 Taylor polynomial is x minus x cubed over 3 factorial plus x to the 5 over 5 factorial. And then the order 7 Taylor polynomial for sine x is going to be x minus x cubed divided by 3 factorial plus x to the 5 divided by 5 factorial, and then minus x to the 7 divided by 7 factorial. So we're taking more and more terms. So this is an example of Taylor polynomials for the function sine x centered at 0. Okay, so this notation, right? So t sub n x, what this means is that we're truncating the series up to x to the power of n. So this means truncating the Taylor series up to and including the term with x to the n. Okay, so that's why t sub 7 goes all the way until x to the power 7. And the point is that basically, like, as you let n get larger, you're taking more and more terms. So when you have t sub 9, it's going to go up to there's going to be even more term. So as n gets larger and larger, you get a better and better approximation of the original function. So in fact, I have a little demo to show you. So recall that these polynomials are supposed to be representing or supposed to get closer and closer to sine x, because, I mean, sine x is actually equal to this power series, which means that if you truncate it at some point, like we did here, for example, t sub 7, well, it's not going to be exactly sine x, because I'm not including all the other terms, but it will be a good approximation. So what we're hoping to see in the graphs that I'm about to show you is that t1 is going to be a line that's going to represent the function sine x. That's going to look like a function sine x, but it's going to be kind of a bad approximation. And then t3 is going to be a slightly better approximation, and t5 of x is going to be even a better approximation for sine x, and so on. So here's the graph of sine x here, right here, in red. And now I'm going to draw the graph of y equals to x. So this is the first Taylor polynomial, and we see this nice line here. So we see that around 0, it represents it quite well. But sort of, if you go a little away from 0, it's not as nice. Now the second, the t sub 3, Taylor polynomial of order 3, is this one here. So if I graph this, it's the green one, and it's better than the line because it kind of follows kind of like the line, but then it captures a little bit of the curvature of the function here as well. And then we have order 5 Taylor polynomial. So it's even better. And then we have order 7 Taylor polynomial. It's even better. See, the last one here is given in black, and it goes all the way until here. So hopefully this gives you a nice graphical evidence that as you increase n, the nth order Taylor polynomial will get closer and closer to the function. Okay, so let's move on and talk about Taylor series in general, and not centered at 0, but arbitrary center. So general Taylor series. So this is arbitrary center. So Taylor series for a given function, f of x, centered at x equals to a, for a is any number, so x equals to a. So a here is any center. So before a was 0, but now a could be anything, is the following. So we have n goes from 0 to infinity. So we have this factorial term again, but it's the nth derivative of the function evaluated at a divided by n factorial. So this is the coefficient. And then the thing you're multiplying is no longer x to the n, it's x minus a to the n. And this, what we're hoping, is that will equal to the original function f of x. And in fact, this does happen on a neighborhood of the center a. So usually one can use the ratio test in these problems. Usually one can use the ratio test to conclude that the Taylor series, to deduce that the Taylor series converges for all x satisfying x minus a less than r. So this r here is known as radius of convergence. And actually it could be infinity, so r could be plus infinity, in which case it's the nicest situation, because then, I mean, x minus a less than infinity is true for every x. So if the radius of convergence is infinity, which does happen, for example, when you have the function e to the x, then in fact Taylor series converges everywhere, and it converges to the function value f of x. But r could be a real number, and so the point is that this inequality can be rearranged to look like this. So instead of writing x minus a in absolute values less than r, that's the same thing as saying x minus a is less than r and bigger than minus r, which you can rearrange by adding to three sides of this inequality, adding a to all sides, and then you get a minus r is less than x less than a plus r. And what that means is that x must belong to the interval a minus r, a plus r. See, this interval here is called interval of convergence, and it's symmetric around the center, and that's why a is called the center. So note that this is known as interval of convergence. So interval of convergence, namely at this interval a minus r, a plus r, is symmetric around a. It's symmetric around x equals to a. And so this justifies the use of the word center for the symbol a. That's because, so for x equals to a. So that's why we call a the center. That's because if you look at a minus r and a plus r, a is exactly in the middle, right? So you have this interval, a is here, and then you have minus r here. Well, you have a minus r here because you subtracted r from it, and then you add r to it, you get a plus r. And so being on this interval from a minus r to a plus r means, well, a is exactly in the center. Okay, so again, sometimes to check at the endpoints, you might have to do manually. You might have to plug in a minus r and see when x is a minus r, exactly if this series converges or not. So endpoint behavior, it's not guaranteed whether it will converge or not, but it's at least the open interval, and sometimes it might include the endpoints. So sometimes even the endpoints, x equals to a minus r or x equals to a plus r, could be in the interval of convergence, could be in the interval of convergence, but for these ones you have to do manually. A ratio test will be inconclusive for these values. Convergence needs a manual check. So basically, like if you try to use the ratio test again on these values, you're going to get the limit of am plus 1 divided by an to equal to 1. And that's why ratio test is exactly conclusive at the endpoints. So you will see in your homework when you do problems like this what happens at the endpoints. So let me do an example of a Taylor series. So here's an example. So let's find a Taylor series for the following function. For the function f of x equals to cube root of x around x equals to 8. Okay, so this means the center is 8. A equals to 8 is the center. So basically we have the graph of this function. So this is the graph of the function. It looks like this. And so at the point x equals to 8, this is x and this is y. And if this is the graph of the function f of x equals to cube root of x, well, when x is 8, cube root of 8 is just 2. So the y is 2 here. So we have this point here. Of course, the graph continues. And we want to understand, we want to write down a power series that represents this graph, and especially converges to this graph, converges to this function near the point x equals to 8. So what we're going to do is we're just going to apply the definition of Taylor series, right? And in the definition of Taylor series, we need to figure out the nth derivative of the function. So it might be useful to compute the nth derivative of the function for any n. Nth derivative of f of x equals to cube root of x. Okay, so another way of writing cube root of x is x to the power of 1/3. And so this is going to help us in computing the derivatives using the power rule. Now, once we compute the nth derivative and then we evaluate the nth derivative at the center. Evaluate it at x equals to the center a, which is 8 in this case. Okay, and this is because the formula suggests, right? This is because the formula for the nth term, coefficient of the nth term, is the nth derivative of the function evaluated at a divided by n factorial. So really need to figure out the nth derivative, and we have to plug in the center into it. So let's write down the zeroth derivative. Well, the zeroth derivative of the function is the function itself. This is just f of x, which is just x to the power of 1/3. Okay, so the first derivative of the function is, if you use the power rule, it's just 1/3 times x to the power of 1/3 minus 1. The second derivative of the function is 1/3 times 1/3 minus 1 times x to the power of 1/3 minus 2, because it's this exponent here, minus 1. If you subtract 1 from this exponent, you get 1/3 minus 2. So the minus 1 becomes a minus 2 because you subtracted 1. And then the third derivative becomes 1/3 times 1/3 minus 1. Now I bring the exponent down, so 1/3 minus 2. And then I subtract 1 from the exponent, so it's 1/3 minus 3 here. So I took the current exponent and I subtracted 1 from it. So if you continue in this fashion, what you end up getting is that the nth derivative of the function is, well, you just keep multiplying by these terms. So you have 1/3 minus 1 times 1/3 minus 2 times 1/3 minus 3, and so on. The last one is 1/3 minus, well, it's 1 less than n minus 1. See, like this number here, the last one, minus 2 is 1 less than 3. This is the third derivative. And so it's n minus 1 here because we're taking the nth derivative. And then it's x to the power of 1/3 minus n. Because you see this minus 2 matches with the second derivative, minus 3 matches with the third derivative, so minus n matches with the nth derivative. And now what we have to do is we have to evaluate these derivatives at 8. So, you know, the function value at 8, well, this is just 8 to the power of 1/3, so cube root of 8, which is 2. We now have to compute the derivative at 8. And that's, well, I'm just going to copy it. So it's 1/3 times, so instead of x, right, this is x, this is f prime, right? This is f prime. So instead of x, I plug in 8. So this is just 8 to the power of 1/3 minus 1. Okay. So this here, second derivative evaluated at 8 is 1/3 times 1/3 minus 1 times 8 to the power of 1/3 minus 2. So again, I'm just plugging it in 8 into x. So the third derivative I evaluated at 8 is just 1/3 times 1/3 minus 1 times 1/3 minus 2 times 8 to the power of 1/3 minus 3. And finally, the nth derivative evaluated at 8, and this is the most important one because this is the formula, is 1/3 times 1/3 minus 1, 1/3 minus n minus 1 times 8 to the power of 1/3 minus n. Okay. So that's it. We computed the nth derivative of the function and evaluated at 8. We got something like this. Okay, so this means the Taylor series. So, thus, the Taylor series that we want is the following. So f of x is going to equal to the following. So we have n going from 0 to infinity. And according to our formula, I have to take the nth derivative evaluated at the center, divided by n factorial, and then multiplied by x minus the center to the power of n. Okay, and this is good because we have already figured out what the formula is. We figured out what the formula is for the nth derivative of the function evaluated at 8. And so I just take this thing that I've circled in blue, and I substitute it into here. Right here. So what do I get? I get that my Taylor series looks like this. Sum n goes from 0 to infinity. Okay, so what you have is 1/3. So you have 1/3 times 1/3 minus 1 times 1/3 minus 2 1/3 minus n minus 1, and then you have 8 to the power of 1/3 minus n. That was the nth derivative evaluated at 8, and then you have to divide all that by n factorial. times it by x minus 8 to the power of n. Now we can simplify this a little bit by, we'll copy it down, so I have 1/3 times 1/3 minus 1 times 1/3 minus 2 times 1/3 all the way until 1/3 minus n minus 1, and then I can write this as 8 to the 1/3 divided by 8 to the n, because I have a negative n here, which means it goes in the denominator, and I also have an n factorial here. I also have this term x minus 8 to the n. So I can simplify it even further by noting that this is the same thing as so I have this numerator, and I have n factorial here. Now, 8 to the power of 1/3, this thing here is just 2, because it's just a cube root of 8. Cube root of 8 is 2. So right here, this thing here is 2. So times 2. And then this term I can just combine. This part I can just combine. If you combine it, so again, right here, this was 2. That was 2. Let's write it a little better. And then this blue thing I can just combine and obtain x minus 8 divided by 8 to the power of n. So this is my Taylor series. Okay. So now I leave for you to use the ratio test on this Taylor series to figure out for which values of x does this series converge. So ratio test tells us that the series above, Taylor series above, so converges. So whenever this thing here, x minus 8 divided by 8, is less than 1. So this part here being less than 1, this just comes from the ratio test, basically. You have to compute limit of the n goes to infinity, limit of am plus 1 divided by an in absolute values, just like in the ratio test, and then you want that limit to be less than 1. And what you're going to find out is that this part coming from the numerator and n factorial, this part will basically be 1 in the limit, this ratio, and then the remaining part is just going to be this term here. So you want that limit, which is this, to be less than 1. Because remember, in the ratio test, you're computing the limit as n goes to infinity of the absolute value of am plus 1 divided by an, and you want that ratio, that limiting ratio, to be less than 1 for it to converge. Because if that ratio is bigger than 1, the ratio test tells you that it must diverge. And if that limit is less than 1, it tells you that it must converge. And if that limit is exactly 1, then that ratio test tells you, well, it doesn't tell you anything, it's inconclusive. But anyways, I just want to point out that the reason that you're going to get less than 1 here is because it's coming from the ratio test. Now, this will simplify, well, if you multiply both sides by 8 to this inequality. So the series above here converges every time for every x such that x minus 8 in absolute value is less than 8. I can further simplify this. So every time you have something in absolute value being less than 8, it means that the quantity inside the absolute value is already less than 8, but also bigger than minus 8. And you can simplify this further by adding 8 to all sides of the inequality. So 8 minus 8 becomes 0, and then x minus 8 plus 8 becomes x, and then 8 plus 8 becomes 16. So going from here to here, we just added 8 to every side of the inequality. So that's it. So what we're saying is that it converges, Taylor series converges for each x in the interval 0 to 16. Okay? And so this is the interval of convergence, but endpoints need to be checked as well, plus potentially the endpoints, plus potentially the endpoints, namely 0 and 16. You would have to check if it converges there. And oftentimes when you plug in the endpoints, you either get a geometric series or you get a p-series. Usually get a p-series. So for example, you might get a harmonic series, which in this case would diverge. But notice again that the interval from 0 to 18 it looks like this. So you have 0 here. Sorry, 0 to 16 it looks like this. 0 to 16, and exactly 8 is in the middle. That's why the center 8 is exactly in the midpoint of the interval of convergence. Again, justifying the use of the term center. Okay. So next, I want to give an application of Taylor series to differential equations. So application of Taylor series to differential equations. So I'm going to start with a differential equation that we're actually familiar with. So suppose we have the following differential equation: y prime equals to y, and y of 0 equals to 1. Okay. So in other words, what we would like to find a function. We want to find a function y equals to f of x. Right, we want to find y as a function of x. So y equals to f of x such that what? Well, there are two conditions to be satisfied. The first condition is telling us that the derivative of f is f itself. That's exactly what the condition 1 says, y prime equals to y. It means that whatever this function is that we're trying to figure out, well, it has to have its own derivative. The derivative function should be itself. And there's one more condition, y of 0 equals to 1, which means that the function value at 0 is 1. Okay, but we actually know how to solve this differential equation because this differential equation is separable. This is a separable differential equation, so which we already know how to solve. We have covered this earlier in the course. Okay, so in fact, we know what the solution is. You can probably guess. What's the function whose derivative is itself, and the function value at 0 is 1? Well, it turns out there's only one function, and it's e to the x. So f of x equals to e to the x is the answer. Is the solution, sorry, to this differential equation. Is the solution. And indeed, it's true that derivative of e to the x is e to the x. So and the value of the function e to the x at 0 is 1. So why am I telling you about application of Taylor series? Looks like we have solved this problem already. Well, I'm going to show you another method to solve this differential equation. That's far more general than just applying it to separable differential equations. So the method I'm going to show you applies to a broader class of differential equations that may not be separable. So I'm just showing you this example because it's going to be easier to show the method on this example. But the method I'm about to show you applies to other class of differential equations that are not handled by the methods we have learned in the class so far. So it's called a series solution to differential equations. Which basically means that you try to figure out the solution, so you don't know. Let's pretend we don't know e to the x is a solution. And you write down a potential solution as a series, and then power series, and then you want to find the coefficients, basically. So let me illustrate it. So suppose we don't know the answer above. So suppose we don't know that y equals to e to the x is the solution. And let's find it in a different way. So here's a different technique that we're going to use. So basically what we say is that we write down the potential solution as y equals to a0 plus a1x plus a2x squared plus a3x cubed, dot, 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 and then solve for the coefficients. That's what we have to do. Solve for the coefficients a0, a1, a2, a3. Like, we have to actually solve for all of them. So what we're just doing is that we're representing a solution to the differential equation in a power series form with undetermined coefficients. So a0, a1, a2, a3 are undetermined, but our goal is to figure out what those coefficients should be. So once we solve for the coefficients, well, we're in good shape. Then we have recovered what the solution is. Okay, so how do we solve for these coefficients? Well, we can use the condition y of 0 equals to 1 as a start. What's going to tell us? Well, that's going to tell us what happens to a0. Because if you plug in x equals to 0, you should get 1. So that means 1 should equal to a0 plus a1 times 0 plus a2 times 0 squared plus a3 times 0 cubed, dot, dot, dot. But all these terms, except for the a0 term, is 0 because I'm multiplying by 0 here. So all of them are 0. So all this is 0. That tells me that a0 is 1. So now I've already recovered the first coefficient. So I know what a0 should be. It should be 1, but I also need to figure out the rest of the coefficients. Like, I need to figure out what a1 is. I need to figure out what a2 is and a3 is, and forever. Okay, so we used one of the conditions in the problem, the initial value. Usually, initial value will tell you some information about this coefficient. But now, we haven't used the most important information, which is the differential equation, like y prime equals to y. So we just have to substitute this expression here. We just have to take this expression and substitute it. Substitute this to y prime equals to y, because that's the given key information that must be satisfied for our solution, right? So what I've written here is a potential solution, and I want to investigate that potential solution. What do I know? Well, I know that potential solution must satisfy y prime equals to y. Okay, so we know that y prime should equal to y, right? And then we know our potential solution is of the form a0 plus a1x plus a2x squared plus a3x cubed, and so on, plus. So this is our potential solution. So if you substitute this here, what do you get? Well, on this side, we get the derivative. So let me just write clearly. So I have a0 plus a1x plus a2x squared plus a3x cubed plus dot, dot, dot. I'm taking the derivative, right, because that's y, and I'm taking y prime. That should equal to y itself. So it should equal to a0 plus a1x plus a2x squared plus a3x cubed, dot, dot, dot. Okay. So when you take the derivative of this, well, what do you get? So derivative of a0 is 0 because a sub 0 is just a constant. So there's nothing here. Derivative of a1x is just a1. Derivative of a2 times x squared is 2a2x. Derivative of a3x cubed is 3a3x squared. Let me write one more term. So the next term here should be a4x to the 4, right? That's the next term. So there should be, if we take the derivative of this, it should be 4 times a4 times x cubed, and then there's more terms. There's more terms here, like a5x to the 5, and so on. Okay, so this should equal to the right-hand side, and the right-hand side is just a0, a1x plus a2x squared plus a3x cubed plus dot, dot, dot. But these two expressions should be equal as functions. They're true for every value of x. How could this be? How could it be true that two power series are equal to each other? The only way, sorry, this should be a1x, right? So this is a1x. Okay, so how is it possible that two power series can equal to each other? Well, the only way that's possible is if the coefficients of the corresponding powers of x are equal. So we can now equate the coefficients accordingly. Right, so coefficient of x to the power of 0, well, that's just constant, so that should be a1 should equal to a0. Coefficient of x on both sides must be equal, so 2 times a2 must equal to a1. Coefficients of x squared on both sides must be equal, so 3 times a3 must equal to a2, and so on. That's what we need. Okay, so let's write down what happens when we equate the coefficients. So what we get is a1 on this side, which is the constant term, if you like, it's like x to the power of 0, should equal to a0 on this side, because a0 is the constant on the other side. But we have computed what a0 is already. That was computed using the initial value. So a0 is 1. That tells us that a0 is 1. Okay, so let's look at here. Okay, so when you equate the other one to 2a2, that's the coefficient of x on this side, should equal to a1, because that's the coefficient of x on this side. But we have already figured out what a1 is from the previous stage, right? So you kind of work iteratively. So we know what a1 is from this stage. Actually, let me just write a little arrow. So this allows me to solve for a2. So a2 must equal to 1/2 a1. I just divide both sides by 2. But I know what a1 is from the previous line. It's 1. So a2, I also figured it out. It's 1/2 times 1, so it's 1/2. That's it. So we found a0, a1, we found a2. Okay, let's keep going. So let's equate coefficients of x squared on both sides. So you should get 3a3 should equal to a2. And that should tell us what a3 is. a3 is 1/3 a2. But look, I already figured out what a2 is. It was 1/2, right? From the previous line. So it's 1/3 times 1/2. If you like, it's 1 divided by 3 factorial. And if you like, this is 1 divided by 2 factorial. Okay. So let's keep going. So next one is going to be 4a4 should equal to the coefficient of x cubed on this side, a3. And so I get a4 should equal to 1/4a3, and that should equal to 1/4 times, well, I know what a3 is from the previous line. I've computed it. It's 1/3 factorial. If you multiply 1/4 with 1/3 factorial, it's the same thing as 1/4 times 3 factorial, which is 4 factorial. Okay, so we see the pattern, right? So a2 is 1/2 factorial, a3 is 1/3 factorial, a4 is 1/4 factorial, so we expect a5 is going to be 1/5 factorial, and this is indeed true. And if you keep going, kind of after n steps, you have n times a sub n. If you just follow the pattern, it should be a sub n minus 1, and that means you can solve for a sub n. A sub n is 1/n times a sub n minus 1. But by the previous line, we would have obtained that a sub n minus 1 is 1/n minus 1 factorial. And if you multiply 1/n with 1/n minus 1 factorial, you get 1/n factorial. Okay? So that's it. We actually figured out what the coefficients are. So a sub n is 1/n factorial for each n. Okay, so coefficients have now been recovered. Okay. But that's exactly what we wanted, because we wrote down the solution in this form. This was our solution, right? This was our solution. So once we know what ANs are, this means that the solution, thus, the solution to our differential equation is, so y equals to a0, so it was y equals to a0 plus a1x plus a2x squared plus a3x cubed, dot, dot, dot. And so this is the same thing as 1 plus x plus, well, we figured out what these coefficients are. So, right, so a1 was 1/1 factorial, which is 1. a2 is 1/2 factorial times x squared. a3 is 1/3 factorial times x cubed. a4 is 1/4 factorial times x to the 4th. Okay, but we have seen this series here, this power series here, right here, is the Taylor series for e to the x. And that's why this is e to the x. That's kind of amazing, right? Like, we figured out what the series solution should look like, and we found these coefficients, and now we'll repackage what the Taylor series looked like with our previous knowledge into e to the x. So that's it. So y is equal to e to the x is our solution, as was previously observed much earlier. As I said, e to the x is certainly a solution to this differential equation because it's its own derivative, and e to the 0 is 1. And in homework, you will see similar problems to this with more complicated differential equations. Okay, so let me show you another application of Taylor series. So computing limits with help of Taylor series. Okay, so let's do an example. So let's try to compute the following limit. Limit as x goes to 0 of cosine x minus 1 plus x square over 2 factorial divided by 3x to the 4th. So when you see a question like this, and you see cosine x, and you see all these other polynomials, it might be a good hint that you might want to use Taylor series for cosine x instead of dealing with cosine x, which might be complicated. So solution, we can replace cosine x with its Taylor series, right? So using the Taylor series for cosine x centered at 0, Taylor series, cosine x equals 2. So what's the Taylor series for cosine x centered at 0? So we saw this in the previous lecture. It's 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial plus, and so on. Alternating powers, even powers of x, and then you're dividing by the same exponent factorial at the denominator. So one thing worth noting is that cosine is an even function, and that's why you expect to see even powers of x in its Taylor series. Okay, so why is this useful? Well, if you just replace cosine x with this expression in the limit, it'll make our lives easier. So the limit as x goes to 0 of cosine x minus 1 plus x squared over 2 factorial divided by 3x to the 4th. Well, this is equal to limit as x goes to 0. Well, let's write down. So the Taylor series for cosine of x, it's 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial. Let's write one more term. So x to the 8 over 8 factorial, right? And then minus dot, dot, dot. That's my cosine x here. And then I have minus 1 plus x squared over 2 factorial here. And I'm dividing this by 3 times x to the 4th. Now what we notice here is that some cancellations happen in the numerator. So this 1 here cancels out with this minus 1, and minus x squared over 2 factorial cancels out with the plus x squared over 2 factorial. And this will be the key. And so what we get is that limit x goes to 0, at the top, the first surviving term is 4 factorial, x to the 4th over 4 factorial. And then you have minus x to the 6 over 6 factorial. And then I have plus x to the 8 over 8 factorial. And then I have a minus dot, dot, dot. And then these terms are canceled. And I divide this by 3 times x to the 4th. Okay. Now, I can cancel out x to the 4th from both sides. So in this step, I'm going to cancel. Going from here to here, I'll cancel x to the fourth from both sides. And the way you achieve that is, so the x to the fourth at the top, that one becomes a 1, get 1 over 4 factorial, minus x to the 6, you have to divide this by x to the fourth, and you just get x squared over 6 factorial. And then x to the 8, you have to divide this by x to the fourth, you get plus x to the fourth minus 8 factorial, and so on. So here you have more higher powers of x, and it's divided by, well, if you divide the denominator by x to the fourth, you just get 3. Okay, but this limit can be computed by just plugging it in 0 into x. And so if you just plug in 0 into x, there's no issue, right? So you just get 1 over 4 factorial divided by 3, because all these other terms are 0. So if you like, it's minus 0 plus 0 minus 0 dot dot dot, they're all 0. So you just get 1 over 4 factorial divided by 3, which is the same thing as 1 over 3. So let's see, it's 1 over 4 factorial times 3. 4 factorial is 24. So 1 over 24 times 3 is 1 over 72. And that's the answer. Yeah, I guess I should have noticed, I guess I should have said this earlier, but in this problem, you can't just plug it in x equals 0, because you will just get 0 over 0. If you plug in x equals 0, you're going to get 0 in the denominator for sure. And in the numerator, you're going to get cosine 0 minus 1 plus 0. Well, cosine 0 is 1. So 1 minus 1 is 0. So 0 plus 0. So then if you plugged in x equals 0, you get 0 over 0. So you could use L'Hopital's rule for this problem, but sometimes L'Hopital's rule, you would have to use it like 4 times back to back. But I think this method is cleaner. And there could be problems where L'Hopital's rule wouldn't work, but the Taylor series approach would give you a clean, clean way of seeing what happens in the limit. Okay, so let me do another problem. So this is just a problem that's similar to something that you have in the homework. So the question is, write Taylor series for the function f of x equals to sine x at x equals to pi over 2 as, so this is our Taylor series, c sub n is the coefficient x minus pi over 2 to the n, and then this is n goes from 0 to infinity. So the question is, find the first 5 coefficients. In other words, we need to find c sub 0, c sub 1, c sub 2, c sub 3, and c sub 4. These are the coefficients we need to find. Okay? So to find the coefficients of the Taylor series, well, we just have to remember what the formula is, right? So the solution is the following. So recall that the Taylor series centered at x equals to pi over 2 should take the form sum n goes from 0 to infinity of nth derivative of the function evaluated at pi over 2 divided by n factorial times x minus pi over 2 to the power of n. Okay, but we know this should be, according to the problem statement, c sub n times x minus pi over 2 to the n. This is according to the problem statement. According to, so let me just write this a little better. According to the problem statement. The CNs are defined as being coefficients of the Taylor series. Well, that tells us that we can just match the coefficients, right? So c sub n must equal to this quantity here. So this tells us that c sub n is just the nth derivative of the function evaluated at pi over 2 divided by n factorial. So here, the function is f of x equals to sine x. So in other words, to find these c sub n's, the coefficients for the first 4 values, or 5 values, we need to figure out the nth derivative of the function sine x and then evaluate it at pi over 2. Okay, so let's just find the derivatives and then divide by n factorial. So we just have to find the derivatives of the function. So the 0th derivative of the function is just the function itself, which is sine x. And remember, we have to also have to take the evaluate the 0th derivative of pi over 2. And if you evaluate sine of pi over 2, you just get 1. That tells you c sub 0. Well, by definition, c sub 0 should be the 0th derivative of the function at pi over 2 divided by 0 factorial. Well, 0 factorial is 1, and this is 1, so we just get that c sub 0 is 1. Okay, so first derivative of the function is, well, cosine. And then the first derivative evaluated at pi over 2 is 0. Because cosine of pi over 2 is 0, which means c sub 1. By definition, c sub 1 is nth derivative, which is 0, divided by 1 factorial. So it's just 0. And let's just do the others. So the second derivative is derivative of cosine is minus sine x. If you evaluate the second derivative at pi over 2, well, sine pi over 2 is 1, but it's minus sine, so you just get minus 1, which means c sub 2 should be minus 1 divided by 2 factorial. So this is 2. 2 factorial, which just becomes negative 1/2. And then the third derivative is the derivative of minus sine x, which is minus cosine x. And then you evaluate the third derivative at pi over 2. Well, if you evaluate cosine at pi over 2, you just get 0. And then so c sub 0 should be 0 divided by 3 factorial, which is still 0. And then the fourth derivative is derivative of minus cosine x. Well, the derivative of cosine x is minus sine x, and there's an additional negative sign. So derivative of minus cosine x is plus sine x. So we're back to the first one, the 0th one. So the fourth derivative evaluated at pi over 2 is sine of pi over 2, which is 1. And then c sub 4, by definition, is the fourth derivative evaluated at pi over 2 divided by 4 factorial. So it's 1 divided by 4 factorial. So it's 1 over 24. And so these are the coefficients that we seeked. C sub 0 is 1. C sub 1 is 0. C sub 2 is negative 1/2, c sub 3 is 0, and c sub 4 is 1 over 24. And this answers the question that was in the problem, finding the first 5 coefficients. And this ends the lecture 24.